Swayam Prabha. Digital India. Educated India.
Dear students, so far we have studied the mutually coupled circuit where two or more coils are mutually coupled and they share mutual inductance and the voltage get induced. So now next we'll extend that concept to the case of transformers. So in case of transformers we understand that there are two coils which are mutually coupled. So suppose these are the two coils. So when these are mutually coupled, we assume that this current I1 and there is a current I2. The voltage which appears the terminals is V1 and V2. Now if we write the KVL equation, which is on this side, the voltage V1 can be written as L1 di1 by dt, and this will be plus M di2 by dt. Similarly, if we write V2, it can be written as L2 di2 by dt plus M di1 by dt. Okay, so this is how the mutually coupled equations are written. Now in case of transformers, the current is assumed as, so what I'll do, I'll just quickly redraw. So this is I1 and this is I2. Okay, so this is how the transformer currents are drawn, or the reference is taken. So here I2, suppose this is can be written as I2 prime. So I2 is nothing but negative of I2 prime. Okay, now substituting these values here, in case we can write V1 as L1 di1 by dt minus M of di2 by dt. Now this is di2 prime. Similarly, V2 will be L2 di2 by dt, and this will be di2 prime, then negative will appear, plus M di1 by dt. So these equations are written with this current direction, and these equations are written with assuming the current direction leaving the dot position in the coil 2. So this is L2 and this is L1. Now suppose this is equation 1 and this is equation 2. Now divide equation 1 and 2. We get V1 by V2. Basically we want to calculate V1 by V2. So if you do so, this will be written as L1 di1 by dt minus M di2 prime by dt by L2 di2 by dt plus this will go to prime side, then M di1 by dt. Okay, so this is the equations which are written in the division form. Now L1 is nothing but N1 square by reluctance. This is a total reluctance, right? So N1 is the number of turns which is in this direct side, like, and number of turns in L2 is in the coil L2 is N2. Okay, so now L1 is N1 square by R, and similarly the L2 is nothing but N2 square by R is the reluctance again, and M is nothing but N1 N2 by R. This is a mutual inductance, right? So this is how this is written. Now substituting these two values, we get N1 square by reluctance di1 by dt minus N1 N2 by reluctance di2 prime by dt divided by, just substituting N2 square by reluctance, di2 by dt, one goes prime, negative will appear, plus, so from here M again will write as N1 N2 by reluctance. So if from this is taken as common, and from bottom if you take this as common, it will be N2 di2 by dt prime negative plus N1 di1 by dt. So this is the equation which we get. Now what you see, the left hand term is v1 by v2, and this is common, it get cancelled, and r also get cancelled. So v1 by v2 is turned up as n1 by n2. This is a very important relationship, with assumption that there is no leakage and whatever the flux which is being generated is entering this side, because this is the kind of coupled coils. So M is taken as a mutual inductance. So if K is given, so this will decide the leakage side, right? So then we have to take M as root L1 L2 times of K. Okay, so now this is the equation. So if you observe what is the inductance, ideal inductance, so L1 is nothing but N1 square by R, and R is nothing but L by mu times of A. Okay, so ideally the mu should be infinity, which means that the reluctance should be 0, close to 0. When reluctance is very low, inductance will be infinity. It means that ideally L1 will tend to infinity, similarly L2 will also tend to infinity. So these are the condition for ideal transformer when L1 and L2 are quite high. Okay, so with this let us go into the detail of the winding. So clear, I'd like to mention one thing. Here you have seen the mutually coupled coil case, we have taken the polarity of the dot notation as mutual inductance positive when both the currents are entering. But in case of transformer, we assume I2 prime which is leaving the current, and we see that the relationship. So now onwards, do not get confused when we mention transformer as the so primary side or the one side of the transformer, the current will enter, and other side the current will leave in case of a transformer, and it will be taken as a reference now onwards. So it is basically an assumption which we make. So now I1 this and I2 and this is V1. So this is the reference which will be taken care for the transformer case, not in the mutually coupled circuit. So this explanation basically will tell you this reference get nullified when we talk about V1, V2, and now onwards we'll be taking this assumption when the current enters. So do not get confused with the current direction of I2. Okay, so now let us talk about the case of transformer in little detail. So this is just a representation. So what is the principle of operation of transformer? Okay, principle of transformer operation. correct? So basically a transformer is a static device which consists of two or more stationary electric circuit interlinked by a core. So this is the iron core, which is having two coils or windings which are being okay. So this is the core. So this core will be having a common magnetic circuit. So this core basically provides the common magnetic circuit to the primary and secondary side. So this is one coil and another coil will be this. So we assume that the voltage which is appearing across the winding is EMF induced, or we call it E1, and the current I1. Here it is E2, the current is leaving I2. So do not get confused now with the direction of this number of turns. We can assume N1 and N2, and the flux which is flowing in this is limited to this core. Now we'll assume some condition. So what happens in this particular case? The transfer of energy takes place from this coil side. So this side, suppose your load is connected, and this side your supply is connected. Okay, so V1, and the voltage which appears across this V2. Okay, so what the role of transformer is to transform the energy from one voltage level to the another voltage level. So basically V1 by V2 is equal to E1 by E2 is equal to N1 by N2. So this is a transformation which takes place through this magnetic circuit, and the magnetic link is being provided by the core. So the condition for the ideal transformer is no losses in the electrical or magnetic circuit. So there are no losses. Coils are coupled, they share mutual reactance, voltage get induced. So now next we'll extend that concept to the case of okay, so there is no losses. One assumption is that the whole flux, so whatever the flux which is being flowing is linking to the another winding. So the flux which is being produced by the current I1 is leading or linking completely to the secondary winding. It means that there are no leakage flux. Okay, no leakage flux, or basically the permeability of the core is infinity. You can write it as third number, otherwise the permeability of the core is very high or ideally infinity. Correct. So now onwards, when we see a symbol of a transformer like one winding, these two parallel lines, and another winding, it means that these two coils, which is like having turned N1 and N2, so these coils are linking using a magnetic core, which is iron core basically. Mutually coupled equation. Case of So these lines represent the iron core of a two-winding transformer. Primary side is N1, secondary is N2. Or normally it is based upon the voltage also, we call it low voltage line or low voltage side or high voltage side, depending upon the voltage ratio. Okay. So the energy is being received from the primary side and fed to the load which is connected to the other side. So this is basically a motor or in general some load. Okay, so this is the connection which we will be assuming for I2 and I1. Okay, so now let us write down the EMF equation of a transformer. Okay, so suppose the main flux which is flowing in this circuit, this phi, because the voltage applied is sinusoidal, so the phi can be assumed as pi m sin omega t, okay, which is varying sinusoidally. Then the induced EMF using Faraday's law, the induced EMF is nothing but negative of d phi by dt. The negative comes from the Lenge's law. So we can write this as n d phi by dt, because their number of turns are n, which will be minus n d of dt by and it is nothing but minus n omega phi m cos of omega t, and it can be written as n phi m omega sin of omega t minus pi by 2. This is induced EMF. So here you can clearly see there is a phase angle difference between the flux and the induced EMF. So the induced EMF basically can be written as EM of sin omega t minus pi by 2. This EM, the maximum induced field is n phi m omega, which is nothing but n phi m is then 2 pi f. Omega is nothing but 2 pi f, and the RMS value of E will be 2 pi by root 2 n pi ml. Okay, and that turned out to be 4.44, which is very famous equation times of phi m f n. So this is RMS value and the maximum value is this. So from here E1 will be nothing but 4.44 phi m f n1, and E2 will be nothing but 4.44 pi m f n2. From here we can see E1 by E2 is nothing but n1 by n2. With assumption that okay, there is no leak. So this is the voltage which is being given as a ratio of the turns of the mutual inductance. If K is given, one of the winding to the another winding. So this N1 by N2 is known as turns ratio. Now one thing you can point out that the phi in E1 and phi in E2, sorry, the F, the frequency. So in transformation, frequency remains constant. Frequency remains constant. So whatever the energy transfer from primary coil to the secondary coil is happening, that is happening without the change of frequency. So this is one of the important things you can note down. Now, if we look at the kind of ratio, the turns ratio. So just for an idea, if N1 by N2 is greater than 1, it means we have taken the polarity of the dot node. N1 is greater than N2. So the turns in the secondary side is less. So this is in terms as step down transformer. So it is basically reducing the voltage at the secondary side. Similarly, if N1 by N2 is primary side or less than 1, which implies that N1 is less than N2. It means N2 is greater. So this is step up. Reference now. It is basically an assumption transformer. And if N1 by N2 is equal to 1, this is known as auto transformer. This is the reference. Okay. Not the mutually coupled. This explanation basically will tell you. And these kind of transformer where electrical isolation is required, or we need to separate out one part of the circuit from the another part of the circuit for the sake of protection of some element or component, we use auto transformers. So in case of home inverters or stabilizers, we use isolation 1:1 transformer in general, which provides safety to the element. Okay. Now if we go and think of little bit the construction of a single phase transformer, so let us consider now single phase transformers. So basically a transformer is a static device which consists of two or more. So after the theory, the transformers which is being single phase have a construction in terms of magnetic core. So the core is basically a thin sheet of metal or iron. So this is basically, if you see, it is having very thin sheet. Okay, so this is not a solid core. It has very thin laminations and they are insulated from each other with enamel or some oil paint. So these are the enamel coated thin sheets. So these are which is known as laminations. So this is to avoid the eddy current losses. So if they get a large area which can conduct, the circulating current in the circuit will cause the losses and the heating of the coil, the heating of the core, sorry. So that core will get heated up. So to avoid that, we use thin laminations to reduce the eddy current losses. And the material which we use is like silicon steel or other metals to avoid the hysteresis losses. That is the magnetic property of the material. So the construction basically can be of core type. Like this is the core of transformer. It is having a two vertical legs which is known as limbs. So this part is known as limbs. What happens in this place? And this part is known as yoke. The transformer takes place. Okay, so this is small idea about the this side your supply is connected. transformers. So in case of a distributed winding, so normally the high voltage winding or the low voltage winding are kept. So one side will be having one winding here and other winding on this side, right? So and the flux will flow in the thin sheets of like silicon steel or some other material which is having low hysteresis losses. So this is the flux flow. Okay. So in this case, the windings are placed on the limbs. Core type mein, the windings are basically the coils are placed in limbs. And to avoid the insulation, so what they do, they normally place the low voltage close to the core. So if you see the cross section, you see here some insulation, then there will be one winding, and there will be another winding. So this is basically insulation, and the dark line thing this is low voltage winding and this is high voltage winding. This is HV and this is LV. So this is basically around the core. So this is a core type transformer. Current is assumed as okay. So in shell type transformers, both primary and the secondary windings are wound on the central limb. So the construction is little different. So you have a section where you have central limb, right? So you have a limb in the center. So this is central limb, this is left, this is right limb, and this is a yoke. Okay, so this is the nomenclature of the sections which are being. So this is limb. Values here in case we can. So the windings are placed alternatively, low voltage and the high voltage. So suppose there is a one winding, above that one more, and they're like such stack of winding which will be in terms of disk. Okay, so they are like at the bottom there is a low voltage winding, then high voltage, and again low voltage winding, then high voltage, and then again low voltage winding. So they are like low voltage winding, the high voltage winding, and the flux produces and flows in the two part. So one is this side and another is to this limb, right side and left limb. So this is the construction of shell type transformer, and this is a construction of core type transformer. Okay. So in these transformers, when we talk about ideal transformers, so as we have mentioned, there will be a primary winding, right? So if we consider a core type transformer, okay, so let us consider one core type ideal transformer. So suppose there is a transformer which is core type and having ideal characteristics. So what are the ideal characteristics? So ideal characteristics means the windings which are being used are having no losses. Okay, so ideal transformer L1 and L2 are quite high. First is no losses. Okay. With this, let us go into the in electrical or magnetic circuits. Here you have seen coupled coil case. We taken the polarity of the dot. The second is no leakage flux. Conductance positive, and both the currents are entered. But in case of transform, assume I2 prime which is leaving the current. Relationship. Then now onwards, there is no not get confused core losses, right? Or which is there in this. So no leakage flux, and the material primary side or side of the current will enter. other side the current will, in case of a transformer, it will be taken as reference now. It is basically an assumption as now mu which is tending to infinity. Okay, so the core material which is having permeability which is tending to infinity, or ideally it is infinity. This is the reference for the all practical purposes. So now it has, suppose, given a current I, that current produces a flux, okay, which is moving in the core. So this is the flux direction. Now let us talk about, so when voltage V1 is applied, it takes a current I1 and it magnetizes the core. And when this is magnetizing, it produces an induced EMF which is opposite to the polarity of, so if E1, okay, so and then E2 will be the voltage which is appearing across this, and when there is no load connected, the terminal voltage will be equal to the induced voltage, right? So now take the reference as the flux which we have taken Vm sin omega, phi m sin omega t. So this is phi m. Now this phi m is produced by a current which is being flowed, which is magnetizing current. So that component will be in the phase with the flux. Okay. So this is this is Im or I mu, which is a magnetizing current, and the voltage will be, this core will be having, which is inducing, is E1, which is lagging 90 degree. We have seen in the EMF equation. Now from here E1 and V1 will be opposite due to the Lenz law. Okay, and the E1 is equal to E2 and equal to V2. No, this is only for the unity turns ratio. So E1 and E2, assume that the voltage which is can be different based upon the turns ratio, but E2 and V2 will be equal. So this is the kind of phasor diagram. So this is phasor diagram. Under no load condition, there is no current which is drawn by the secondary winding. This is I2 which is equal to 0. Okay. So one of the interesting thing is which we mentioned was the transfer of energy. The voltage ratio V1 and V2 is related as this side, your, or the secondary voltage is related as N2 by N1. So this is the relation of transformer is primary and secondary voltage and turns ratio. Now since the transformer is ideal, though the input power is equal to the output power. Okay, in this case the input power is nothing but the transformer takes place through this mechanism. The V1 I1 and the output of power is nothing but V2 and I2. Correct? So it means that V1 V2 is nothing but I2 by I1, and you see clearly it is nothing but N1 by N2. So far we have studied coupled circuit. From here we can say that primary volt amperes is equal to the secondary volt amperes. The total volt amperes will remain same, and the current ratio will be the opposite of the voltage ratio. It means that if turns ratio, if we define turns ratio N1 by N2 as A, then this will be A, and I1 by I2 will be 1 by A. Okay. So we can just quickly take one example and see the relationships of voltage, current and power. So for example, a 25 kVA transformer having a voltage ratio then calculate primary and secondary current. Similarly, if you write V okay, so from here I would like to mention that the transformer specification, so apart from this I will mention, so transformers current is assumed as the kVA rating is mentioned, then the voltage ratio V by V, which is nothing but primary voltage by secondary voltage. So these are the two very important ratings of the current transformer specification. So here you can see the kVA is mentioned and the voltage ratio is mentioned. So this is how you have to define the transformer. So what is the voltage ratio and how much power it can carry. So with that, let us look into this example. Now we have to find the current. So kVA is nothing but V into I, right? And this is in K, so you can write it like VI by 1000. So that I1 is equal to kVA by V1 into 1000. So suppose this is 25 kVA, so 25 into 10 to the power 3 by V1 is primary side 3300. So this will come around 7.58 ampere. Similarly, I2 will be nothing but kVA into 1000 by V2, which is around 25 into 10 to the power 3 divided by 400 volt, which will turn out around 62.5 ampere. So you can see the primary side, when the voltage is high, the current is low. When the current is high, the voltage is low. So this is how the power is balanced. So now suppose you want to calculate the EMF induced primary and secondary. Then from the turns ratio, so turns ratio is nothing but N1 by N2, which is nothing but V1 by V2, which is nothing but 400. So 33 by 4. This is the turns ratio. Consider one more example. So suppose 3300 by 250 volt. 50 hertz single phase transformer is built on a core having a effective cross-sectional area of 125 centimeter square. So the core area is 125 centimeter square and 70 turns on the LV side, and LV side turns are 70. Calculate the maximum flux density. So we have to calculate maximum flux density, then we have to find out number of turns on the high voltage winding, number of turns on HV side. Okay, so this is what we have to calculate. So given that E1 is nothing but 3300 volt and E2 is nothing but 250 volts. Frequency is given as 50 Hertz. Area of the core is given as 125 centimeter square, which turns out to be 125 into 10 to the power minus 4 meter square. So using the EMF equation, which is E is nothing but 4.44 IMF NF phi m. So if it is from the primary side, then we can have N1 or E1, and if it is secondary side, we can have this way. Now from here we can also write this 4.44 N2 F BM into area of core. The phi m is converted to BM into AC. Now from here BM is nothing but E2 divided by remaining term 4.44 N2 F and AC. If we put the values and solve, it will come around. Okay, let us write down these values. 250 divided by 4.44 into N2 is number of turns in the mm, 70, right? Yeah, 70 into frequency is 50 into 125 minus 4. So now substituting these values, we get approximately 1.29 Tesla. Okay, so 1.29 Tesla is the flux density. So A option is answered. Now for the B part, where we have to find out the number of turns on the HV side, we can write the voltage per turn, or V1 by E2, nothing but N1 by N2, which implies number of turns on the HV side can be written as E1 by E2 into E2, which is nothing but 3300 by 250 multiplied by 70. So here it will solve, it will be 924 turns. So this is how you can solve the circuits.